I can start talking now.
You can just charade.
I did time mine, so I actually don't know.
Mine's 10 slides. I don't
Mine's 5, and I'm a little worried that like there's one that I have to explain intro. Oh no, mine has a logo. It's more like
The first thing I haven't actually given a presentation about the
I did the smart thing and I put
something.
I put
one
nothing.
flash time.
I have my local research and my modeling research. See, that's a problem we have. I know, I actually have a research.
I know. I did that this semester. Yeah, still, I got a whole bunch more too. I'm actually around for about 3 months.
Maybe we're gonna kick some back. This one's gonna happen.
I will monitor myself. And if I don't get to all the slides,
This is what he's doing. I'll monitor myself. You're gonna keep monitoring myself. 10 minutes. I'm gonna keep you out. Yeah.
We're ready for
Yeah, it's gonna
whenever.
exactly. He's gonna kick us out early.
We're ready
Like,
whenever
but it was
live stream's
8
on.
minutes. And he's like,
yeah, I'm
wow.
trying to figure out if everyone's here. Is Andrea here? She's out there.
I heard.
Yeah, Dan's over there.
Dan is here. Yeah, they're here. A while that Andrea has appeared. I saw Dan. Yes, okay, he's over there. Dan,
All right, we're all going to start. So we're going to be doing some faculty flash talk. So first thing to say is welcome and hello to all of our prospective students who are here. This is really kind of a glimpse of 6 of our faculty's research that we do in our departments. I guess let's see here. To the faculty, like as I said, try to keep it to 10 minutes. We don't want to be here for forever. We do like going home. If you go too long, I will wave my hand and stare at you and eventually just turn the presentation off. So we'll try to keep it there. Our first speaker will be Mayra.
Here we go.
And I'll hand it over to you. Oh, you're timing yourself. All right.
All right, yeah, I'm gonna time myself else. All right, hi and welcome to AOS. This is the satellite birthplace. So if you don't know that, now you do. So I am Mayra Oyola-Merced. I am the PI of this source. I don't like to use my last name. I want to be more inclusive of my students, so I'll explain what source is. Well, it's there. Satellite observations for radiation, severe weather. I do a lot, that's what I'm saying there. So these are some of the areas of my research group. So we specifically look at aerosol radiated impacts, how aerosols are influencing severe weather and climate. Of course, everything is connected with satellite remote sensing. And a little thing that deviates, and I say a little, it's a lot, that deviates from aerosol is the fact that we're also doing aviation weather research. Specifically, I'm looking into clear air turbulence. So a little bit about me, my career path. I got my PhD at Howard University, and a lot of the work that I did was with NOAA. I actually sat at NOAA for a year doing learning how to model and doing dust radiance and modeling for GFS. Then decided to move to California, was there for 3 years at the Naval Research Lab, doing data simulation and radiation for the Navy model. And then I was like, no, Monterey's not for me, let me go south, and went to JPL, one of the greatest places in the world. I didn't want to leave, but I wanted to teach, and ended up here at the University of Wisconsin-Madison. Love it, best job in the world. I'm not saying that because my students are here, but I really appreciate the fact that I get to see all these incredible students become the next generation of scholars. So this is my research group with a couple of people that are not pictured here, but I have 7 undergrads and 3 grad students and 1 that came out last semester. So if you see them around, I'll show some of their research, but feel free to talk to them. They can tell you about the horrible things that we do in our group. So first up, I'll talk about aerosol radiative impacts, and just so you have an idea. My one true love are aerosols, and I started doing dust aerosols when I was in undergrad. So that has carried on with me throughout my entire career. This is actually an example of coming from a publication for the grad student that just finished, Ruby Burgess. So one of the things that we were studying here, is how the advection of something called Saharan air dust can modulate aerosol and aerosol heating rates, and that on its own could actually impact the formation of developing and non-developing African easterly waves. So this is what you see here. We have here Hermine, which was a non-developing African easterly wave, and then Fiona, who, if you have seen or remember the news, became a major hurricane, and we were looking at how the radiation changes could have potentially influenced the development of these African easterly waves. Second, severe weather and aerosol relationship, and particularly what we are looking at is how wildfire smoke, which is a hot topic, is influencing severe weather formation in the Midwest. So if you don't know, now you know, and we didn't know, this is why we had this climatology. We built a 43-year climatology of black carbon, which is a byproduct of wildfire activity, and we ended up realizing that this region gets a lot of black carbon at different times of the year. You can see here the evolution from April to September, and here you see the Midwest and the East Coast. But interestingly, we started this because I have a tornado chaser in my group who wanted to connect aerosols to tornadoes, and we went into the literature and found this paper from 2011. We replicated the case, and so it happened that we saw a lot of aerosol. That particular case is the big tornado outbreak of 2011. The white here are hail, red tornadoes. We see the interaction with wildfire activity from the Yucatan Peninsula. That is not unique for that case. We've seen hundreds, if not thousands, of cases like this over the last 20 years or so. And if you do not believe me, this is a graph that includes the percentage of Storm Prediction Center reports that include aerosol, which are the blue one, no aerosol, and then the total number. And if you follow the graph, the blue ones, you'll see that more often than not, we get 30 to 40%, in some years it exceeds that, related to storm or severe weather events that include aerosol. Now, I'm going great. I have 5 minutes left. Last portion, I just talked to a class about aviation and aerospace weather. And particularly, we're studying something called clear air turbulence. And clear air turbulence is nothing more than turbulence that cannot be detected by our eyes or by radars. So what my research group is doing is trying to understand the mechanisms that drive turbulence related parameters over CONUS, and particularly those that are associated with the jet stream and how those mechanisms have changed over the last 10 years. And the second is we're integrated all sorts of data that we can get our hands on. Reanalysis, pilot reports, satellite data. And the idea is to use machine learning to improve the prediction. And here I have climatological turbulence, but in reality, even day by day, hour by hour turbulence, that's the final goal. So again, here we go. Definition, severe turbulence that occurs without visual warning, normally at flight level. So where we fly at a cruising altitude. We've seen over the last, I would say 5 years or so, that clear air turbulence is a big chunk of all of the accidents or turbulent-related accidents in the United States, about 30%. And that may be associated to climate and climate change. And here what we see is how many parameters in the atmosphere have changed over the last 10 years. Seeing things like, for example, increases in temperature at cruising altitude, which for us that is 200 hectopascals. Here we see the position of the jet changing and going poleward, especially during the month of February. That's why you see that huge red band over there. We see things like how the increase of things like omega, which are associated with vertical displacement of air masses, are changing, especially over the northeast. And finally, we see something called EDR, which is a metric for turbulence used in the aviation community and also in atmospheric sciences. We can see how EDR has changed over the last 10 years or so. We can see increases, particularly here on the northeast. I've talked a lot today. This is the third time I've given a talk, so. All right, 3 minutes left. my final slide, I made it. Okay, so what you see here is actual real data, and I wouldn't say that reanalysis is real data, it's a model. But what you see here is actual data from pilots, from pilot reports. And on the left side, we see all types of turbulence, and we see these beautiful contour lines over here. That's those winds at the 200 hectopascal level. If you notice the color bar, we see here a number over 600, 650, it's almost 700. What that means is that there are 700 monthly reports of all types of turbulence in that grid, versus, for example, in here, that we see clear air. This is about 60. The beautiful thing, and it's not so beautiful, but what we see is the distribution of where this clear air is happening. And we see, again, a lot on the East Coast. And there's a reason why I plotted the locations of all of the major airports in the US and also Madison. Because if we look at the Midwest, we see that we are a hot spot for clear air turbulence. And that's, again, this is reported by pilots. The other thing that is interesting is that the contour lines are actually from reanalyses. And look at how well they align with those reports. So things like this is what we're doing, is trying to understand turbulence generation, and also how is that going to impact air travel in the future. And with that, I'm done. With that.
Before she goes, is there any questions for Mayra, just in case?
Any questions?
Before Dan talks about fish and fun.
All right, bye.
All right.
I'm gonna talk to you.
You guys are all gonna love me for this. There we
Wow.
go. Yeah, sorry.
Last minute.
Last minute. Okay. Hopefully this shows up. If it doesn't, then I just screwed everything up. All right, there we go. Hi, everyone. My name is Dan Vimont. I'm a professor in atmospheric and oceanic sciences. I always say I'm the less good-looking of the two creatures on the image here. This is a Snake River cutthroat caught in an undisclosable location in Wyoming that is also a big fan of AOS. So a little history about myself. I grew up in the Seattle area. So I grew up, I just got to check the time here because we're going to break for dinner here in about an hour, and then we'll come back and we'll do the second half of the talk. So make sure I'm not. Okay, so I grew up in the Seattle area, and I grew up going to the mountains a lot. And so I would go to, my favorite years were years where there'd be 10 feet of snow up in the Cascades in July, and we'd be hiking in that. And those were La Nina years, where we would just get drenched all winter long. And then El Nino years were horrible because we wouldn't get that snow and the skiing would be not as good and so forth. So I developed a lot of interest in understanding climate variability and climate change, and went from Gonzaga University to University of Washington, and then came here in 2003. So my research focused on a variety of things: El Nino, a couple of ocean atmosphere interactions, climate change, and then climate impacts as well. Outside of work, I'm a dad. I got 3 kids, so if you're in one of my classes, you got to deal with all the bad dad jokes and great sense of humor. I like fly fishing. I'm an outdoor enthusiast. Anything dealing with water, I love. I play jazz piano. I'm a former rower, and I got a dog named Lola who, yeah. I love cats. And I'm a big Gonzaga Bulldog fan, so I'd love to talk to you about any of those topics. Here's my research group. There's actually 2 more in the research group who are Jeff and Katie here right now, because I need photos. I work with a couple of postdocs. I've got 4 grad students, and I work with undergrads occasionally as well. I'm also working with some postdocs across campus with some climate research stuff. So Mo is looking at hydrological variability and the changes in hydrological floods in Wisconsin, doing hydrological modeling with Dan Wright. Sagar is does aerosol radiative forcing and cloud radiative forcing simulations and analyses. Allie's looking at ENSO variability and predictability. Jack is looking at aerosol impacts on the North Pacific. And then Katie and Jeff are still figuring out what they're going to be doing. They're new this year, but are looking at ENSO variability using inverse methods. And there's a couple of undergrads that I'm working with as well, or that I've had in the past on a hike through Picnic Point. All right, what do I do? One of the things I look at, one of the areas I like research is ENSO variability. This is a forecast made in April 2023. So this is the state of the system in April 2023. Here is a model prediction that we made of December 2023, and then here's what actually happened in 2023. So we hit that forecast really well. That happened to be the first forecast we made with this model, and after making that forecast, then we were asked to submit these forecasts to the IRI for their global forecast roundtable there. We use both physics-based modeling, so take the laws that govern our climate system, code them up, and run a model forward based on things like conservation of mass, Newton's or Navier-Stokes equations. We also use inverse modeling, where we estimate the model based on the output that it would produce. And so we can use do statistical analyses to back out forms of models that allow us to do dynamical system analyses on ENSO variability. Understanding things like what part of this initial state wants to grow into this. What are the noise structures that can force our the tropical Pacific into growing into ENSO events and so forth. So for fun, I threw in the forecast right now. This is the February forecast from the IRI. Here's our model, and it's saying big La Nina next year. But there's a lot that can happen between now and then. The nice thing about our models is that they are observation constrained. The inverse models are observation constrained, and so we can actually analyze what do we trust in these model simulations. What will the noise do between now and then? It depends on how strong that forcing is and the timing of that noise, but it could do a lot between now and then to drive us away from that trajectory. And then these models are linear, so we can also look at roles of nonlinearity and other state-dependent noise and stuff to see what they would do as well. One of the other areas of research that I'm focusing on right now is looking at seasonality of climate change over the mid-latitudes. This is the trends in SST from model simulations, but observations show the same characteristics, which show that the North Atlantic and North Atlantic has warmed twice as fast in summer as it has in winter. And if we look at model simulations with only greenhouse gas forcing or only aerosol forcing, we see that the mid-latitudes response is larger in summer than winter. What's responsible for that kind of that seasonality? We develop simple models and look at this in looking at the seasonality of our climate system, seasonality of forcing. Turns out sulfate aerosol forcing is entirely a summertime, a spring, summer, and fall phenomenon. Mean state characteristics of the ocean atmosphere system to try and identify this. And last, I'm also involved in looking at climate impacts. We started a program called the Wisconsin Initiative on Climate Change Impacts about 15 years ago, maybe, more than 15 years, that looks at how climate impacts a whole variety of sectors around Wisconsin. This has been really fun for me because it's a community-based organization where it's modeled around complex adaptive systems where the research questions are emergent. It's only through conversation do we really know what kind of questions to ask, what's important for people, and hence what sort of research to do. And so Wikis is now pretty ubiquitous across Wisconsin. And last, yeah, the fish and you are both asking, please let us go. Stop talking. So this fish was happily released back into that stream, and it was happy. It wagged its tail as it swam back. So thank you.
Any questions for Dan before we move to our next speaker? You plug it back in?
I did, yeah, but it's.
There we go.
There we go.
Good to go.
There we go.
Now, we gotta go through all your slides. Oh, no, now you go one back, back one, thank you.
You go.
Right hand.
350. All right, so I am Hannah Zanowski. I'm an assistant professor here in AOS. I've been here for 4.5 years, I think, at this point in time. Time is a-flying, folks. This is me and my amazing research group. I have a couple of graduate students who you probably met today. Marissa, did you go to the lunch? No. Okay, that's all right. Marissa's here now, all right? She's going through some part of her advancement process, so, you know, you won't see her a lot, and that's okay. A couple of graduate students, Jonathan's half mine, half Matt Lazara's, so co-advised, I guess, and then a couple of undergrads as well in my group, and then there's 2 Hannahs now in my group, but I don't have a picture of her yet, and she's also amazing. So I have a lovely little research group here, and we do a lot of different things. So I use climate models to do my research. I'm all about coupled climate models, thinking about how the Earth system works, or the non-Earth system. And so I cover 3 things. So I am a polar oceanographer by training, and so right now I'm interested in asking basically, what the heck is the Arctic Ocean doing, and what is it going to do in the future? All right, I want to know how it's changing, why it's changing, and what is that going to look like. And climate models are a great tool for looking into the future because they're the only tool we have to do that. So I also do paleoceanography, so I am really, really interested actually in very deep time paleoceanography. So Earth has had an ocean for 4 billion years, billion with a B, so it's quite ancient, all right? And so Marissa actually is working on a project with me where we ask questions about the Archean Ocean, which was basically how long the ocean's been, basically from 4 to 2.5 billion years ago. We're interested in understanding the ocean circulation of this time period. For part of that period, Earth may have been a fully covered water world. And so we ask questions basically about how the physical and chemical oceanography of early Earth could impact climate and then potentially the origins of life on our planet. We are not chemists or biologists. Marissa at this point probably knows more chemical oceanography than I do. But I really want to understand the physical oceanography piece of that and how that sets the stage for our living planet, all right? Because almost all of the major things that have happened for milestones for life happened in the ocean first, all right? And so then it's not kind of too much of a stretch for me then to jump into exoplanets. So there are many motions inside our solar system, many oceans, excuse me, and there are many theorized oceans outside of it. And so I want to model those oceans and basically ask questions, what is the role of the ocean in setting the climate and habitability of exoplanets in general, all right? So those are kind of my 3 areas. These are, again, relatively novel for me. My background has really been mostly on Earth and started in Antarctica. Also a really cool place, if I do say so myself. So a couple of research highlights. So me and my graduate student Leo right now are working mostly on understanding internal variability in the Arctic Ocean. And so internal variability is basically the natural or unforced variations in our climate system. And there are kind of an important source of uncertainty when we do climate model projections into the future, all right? And so 2 questions we're asking right now is basically how will Arctic Ocean internal variability change in the future, okay? And then is it actually consistent across climate models, which is the piece that Leo's looking at, right? And so this is, when we think about internal variability, what we really mean, like I said, is this natural unforced variations. But how we represent that in climate models is basically by running the same model a bunch of times and just changing the initial conditions in the atmosphere slightly. And when you do that, every single one of these gray lines here is a single climate model simulation from the same model but with slightly different initial conditions. And what you get is actually that these wiggles happen at different times, are different sizes, and that is a measure of internal variability, so those natural variations, right? So if you go and compare to observations, you actually need them to fall somewhere within this spread rather than comparing them to one of these simulations, one of these gray lines, right? And so what this figure is this is just annual mean sea ice area in the Arctic Ocean. So it's pan-Arctic average, right? And again, each one of these lines represents one of those runs, right? And so we're looking from 1850 here to 2100, right? So over the time period, which not all of our lifetimes, you know, because we should probably be over here. Some of you are past this point, I'm not. But out to 2100, right? I can't believe some of you were born after 2000. We're all getting old. But I'm really interested in understanding that variability. And so I'm curious about basically the spread across all of these members, right? So that's what it is. And so I measure that as basically the standard deviation, and I look at how that changes in time, right? Because it's an important form of uncertainty in climate models. So we're gonna take a small cognitive leap here, and what I'm showing you now is what internal variability looks like in sea surface temperatures averaged over the Arctic Ocean in one climate model. And so this is the spread, right? So it's basically saying the standard deviation across those gray members for a slightly different variable from 1850 to 2100. And now it's broken down by season. Okay, so we have summer here, and goldenrod, fall, winter, spring, right? And what you see over time is this really, really large increase in the spread across ensemble members as you go into the future, right? And so it's actually almost a doubling of that internal variability. So suddenly, as we go into the future in the Arctic, our SSTs, how we predict them, are becoming more uncertain. It's actually becoming more uncertain. And that is because you are getting rid of so much sea ice in the Arctic that you're actually fundamentally changing its mean state. So suddenly the atmosphere is talking to the ocean more, and you're seeing this big increase in the spread in the members. All right, so a couple of other things. So Marissa's doing this amazing Archean ocean work where she's asking about how potential bathymetry could actually impact the Archean ocean circulation. So we know nothing about what the ocean seafloor looked like back in the Archean. It's kind of gone at this point in time. There's very little rock that lives on this earth that still exists from that time period. But if you're an oceanographer worth their actual salt, you will know, or you will learn very soon, thank you, I see you laughing, Gerald, I appreciate that. You will know that bathymetry really matters for the ocean circulation. And so Marissa has been doing some climate model runs where she looks at the meridional overturning circulation in her model with different forms of bathymetry. So this is a flat ocean case versus a bathymetric case, and she's seeing some pretty major changes depending on what bathymetry she puts in the model. All right. Ivana is looking a little bit more at exoplanet oceans, and so we've been asking about whether or not meridional heat transport in the atmosphere is actually always larger than what happens in the ocean. So on our own planet, in modern day, atmospheric heat transport, meridional heat transport, is typically larger than in the ocean in a meridional sense, except roughly near in the equatorial region, they're about equal, right? But then the atmosphere takes over from there. So there are times, though, where if you run exoplanet simulations, especially tidally locked simulations, right, so where you have a planet where its day side is always facing its host star and then has a night side that's always permanent darkness, and a very shallow ocean, you can get a situation where actually your atmosphere is not doing very much meridional heat transport, so this is versus latitude, and where your ocean actually takes over most of that, right? And so we're trying to tease out basically the parameter space of when and where and why that occurs. Okay. I do a lot of other things besides research, all right? I teach a lot, we all do. So I have a research computing class that's all about Python for Earth science data analysis. If that is something that would be useful to you, I recommend you look it up. It's on GitHub. I have all of the course material on GitHub if you just look me up. I teach a Fundamentals of Physical Oceanography class, which is a really awesome class so we can actually learn some oceanography in this department, as well as a couple of other things. I am involved in the Wisconsin Center for Origins Research, which has come online recently. We're one of the founding departments. This is all about thinking about origins of life on our own planet and elsewhere in the universe. And then last but not least, I am responsible for bringing the first RU in our department's 75-year history, called STORM, to this program. It's student training in oceanography, remote sensing, and meteorology. And if you look closely, there may be somebody who looks familiar here. So I will leave it there. I love teaching and mentoring, and I like what I do for many different reasons. But if you have any questions, please feel free to ask. Thank you. Otherwise, we can take it away.
Any questions for Hannah? No. Oh, it's
Let's
me.
go. It's your turn.
It's me. All right. I'm going to turn the alarm off so it doesn't go. We're ahead of time, so that means I can, take like 15, 20 minutes? Is that how this works?
I will kick you in the shit.
So plenty of time.
And you know I'm good for it, so don't even just.
We're good.
It's 3:59, no, it's 4 o'clock exactly. Go.
Okay.
Me too.
So I am Dave Henderson. I'm probably the newest junior faculty here. I started last year. So my research is really focused on impacts of clouds regionally and globally. I am a cloud nerd. I love clouds, what's in clouds, why we have clouds, what clouds do, why they change, are they ice, liquid, anything clouds just makes me happy. That's really what, why I like doing research with clouds. I don't have a group yet because my group is a baby group yet. I have one student, Sarah. Her work is on the second half of what I'll be showing here. But my research is really focused on how we can better understand clouds and their impacts using satellite observations in combination with some sort of modeling data. So satellite observations do a really good job of giving us detailed information of clouds, where they are, what are their vertical structures. Models give us a ton of information about environments in all sorts of spatial and temporal structures. Both of them have assumptions associated with them that we have to take into account, but if we take advantage of the benefits of both, we can actually gain a ton of information of what caused the cloud that we see in the satellite to exist in the first place, or how is it interacting with environments. Can we take satellites' information that we have and put it in a model to better understand how it impacts our circulation. So kind of the first part of my talk is kind of the more larger global kind of scale things that I do with satellite meteorology. Better understanding how clouds in the tropics interact with what we see in the mid-latitudes and higher latitudes. Kind of the main picture here is when we have an anomaly in clouds, whether that be El Nino, La Nina, or something like the Madden-Julian oscillation, where we have a perturbation in cloud fraction in the tropics. That makes air move. It pushes air up. The air has to go somewhere, and eventually it travels back down, and then that goes down, eventually goes back up, and it creates something called a teleconnection, or a wave that moves across the tropics, and eventually moves into the high latitudes. In terms of global model kind of a standpoint, if we want to understand how the clouds are impacting things, in terms of something like atmospheric radiation, there's still a lot of uncertainty of how models represent clouds, and therefore uncertainty in whether they will end up heating or cooling our planet. If there's uncertainty in heat, there's uncertainty in the circulation. And so kind of better how we can understand satellites in combination with modeling to better understand cloud impacts. So I use a set of observations from satellites. Right now, one from CloudSat, which is a cloud radar in space, and Calypso, which is a cloud LiDAR, so a nice big laser that lets us see different aspects of clouds. A cloud radar lets us see more cloud-sized particles, where the radar can see really, really tiny ice particles and aerosols. And we can use these satellites to take nice slices of our atmosphere so we can see the vertical structure of clouds. And so here's a nice zonal anomaly of cloud fraction that we get from these two different satellites. And if we run this information through a radio transfer model, we can derive the amount of heat they give in our atmosphere. So we can see cloud heating from under ice clouds, and with a convection and nice cooling from cloud tops. And so one thing that I want to, I said the last little bullet point here. One thing I really wanted to do with this information is a collaborative project with Professor Stephanie Henderson in this department, is how do we take this heating information with the specific location of the clouds and use a model that she has, which is a dry dynamical model, to essentially say, if any of these clouds change, how would that change our circulation? And so this initial product that we are writing up right now is focused on the Madden-Julian oscillation, which looks at anomalous convection that propagates across the tropics every 40, 60 days. And we can look at our change in clouds associated with the MJO and its associated heating, and see how it moves across the tropics. So these red areas are where convection is increased, and so it's heating the atmosphere, and the blue areas is where we see a decrease in convection, and that's where we're seeing overall cooling. So the cool thing is we can run this through a model. It's called the linear baroclinic model, and we can run it through equilibrium using reanalysis data, so essentially representing our Earth system, and then throw in this heating structure to say, how does the circulation change only due to this change in heating from the MJO? And we can get really cool results like this. And so if we have convection here that's located here in the tropics, this is geopotential height anomalies. So dotted contours or blue colors are showing anomalous low pressure in geopotential height. reds and solid are anomalous high pressure patterns. And essentially what this is showing is that if you include all heating from clouds, from phase change, latent heating, precipitation, and radiative heating, we get what we get in these contours. And if we remove radiative heating, well actually, sorry, if we only use radiative heating, we get the shaded contours. And what this is telling us is that the radiative heating component from clouds, mostly from deep convection and big ice anvils associated with mesoscale convective systems in the tropics, have a large impact in the location of the circulation response. If you don't include the heating from things like ice anvils and cirrus clouds, you actually get a northward drift of this teleconvection response, which would mean that things like atmospheric river events on the west coast of California would be less intense, or anomalous high pressure patterns that can lead to extremes in Greenland or drought in the eastern United States would also be uncertain in terms of that kind of application. So we're really kind of use this as a tool to better understand what specific cloud types are leading to circulation responses, their importance, but also really as a way to better evaluate global models to understand how, if you were to see an uncertainty in one specific aspect of this, what can we tell model developers they should expect in terms of uncertainty in their model. And then on the second half of my research is now very, very zoomed in at the regional level. And it's looking at the impact of the surface radiation budget on the southeast United States and its impact on downstream thunderstorm development. So in the southeast United States, in the summertime and the springtime months, you get these wonderful, initiation of thunderstorms due to no forcing at all. A lot of heat, a lot of humidity. It makes the South just totally comfortable in the summertime, but it gives us really, really cool thunderstorms. Very hard to forecast for. Because essentially you're just random chaos where one starts to blow up, then they all start to blow up just due to interactions with cold pools and things like that. But they are 30 to 40% of their seasonal rainfall is due to these thunderstorms. And so any change in the land, any change in what's going on here, droughts, or maybe more, would change the distribution of thunderstorms. So last year they actually had a huge impact of crop yield having to be removed because there was a drought, thunderstorms didn't happen, and they actually lost a lot of their cropland. So one thing that I've been investigating that Sarah will be continuing on is how we can, go back, disconnect. How we can use geostationary satellite observations to validate different model assumptions and how these thunderstorms grow, to understand what's making them tick. Why do we see one cumulus cloud turn into a thunderstorm versus another one that does not? And we found that the assumptions that models make in terms of the surface radiation balance have a huge impact in thunderstorm growth. This is just the same exact numerical weather prediction model from WRF with one land surface assumption versus another one. And this one on the right produced a more realistic response of thunderstorms, where this one didn't produce them at all. And it really comes down to how the models make assumptions in land types. Specifically in this region here, it does not like me. Over the southern United States, we see a lot of forested areas, and these forested areas have a preferential development for thunderstorm. And so really how the characterizations of trees versus cropland has a huge impact on development. And then using cloud tracking software, I'm being told by my wristwatch I got one more minute, but essentially using cloud tracking, we can track the clouds that we see from geostationary data, track the ones that turn into thunderstorms, do the same thing for models, and investigate how they grow differently as a function of when the thunderstorm started. So pre-thunderstorm growth, we see the same thing. Post-thunderstorm, we see very different characteristics. And we find that it's mostly a function of their land type. So this is surface convergence versus updraft strength here. The forested areas have a much higher updraft strength, which really helps support thunderstorm development. So I'll end it here. What we're working on right now is with the DOE AMF3 field campaign in the southeast United States, where we have a bunch of instruments located all in those forests, and they're looking at the surface radiation budget, they're looking with radars, they're looking up with LiDARs, so we can actually see what the updraft characteristics are over the different land surfaces and thunderstorm development, and really help narrow it down so we can track with satellites and with ground observations to really understand what makes these thunderstorms tick. And that's mine. Are there any questions for me? Fabian.
Looking at the chart you had of like the geopotential height effects of the cloud heating, I was curious, are you guys looking at like a potential relationship between that and like blocking events, just such as with Stephanie?
Yep.
It seems like location-wise, it's very similar to where a lot of like the North Hemisphere blocking happens.
Yeah, and it's looking as a function of where that convection is located in the tropics that leads to those specific events happening. You know, how much of what types of clouds are actually driving to more persistent blocking patterns versus not. And then looking at other forces like El Nino versus La Nina is kind of the next step to see the additional impact of that. Who's next? You. You still got extra time.
Yeah, so we will stick to the theme of clouds a little bit here. Dave and I have done a little research together in the past, and we do have similar interests. In fact, you seem to be getting, with Mayra's talk also, you're getting kind of the satellite radiation core group of faculty in the group here all at once. As I said, Dave sort of already mentioned this. CloudSat and Calypso have been kind of one of the cornerstones of my career. Oh, sorry, let me go back again. I just wanted to say one thing. So my name is Tristan L'Ecuyer. Yeah, sorry. It was on the screen, but I should point it out. And you can find me on the 15th floor, 1511, right across the other side of the building from Dave, actually. I have a relatively large research group. Also, I don't like to have my name in it for one reason, because nobody can pronounce my name, so I don't want people trying to say that. But no, so my group is the Atmospheric Radiation and Climate Research Group, and I have a lot of faces that I could show, and I would probably spend my entire 10 minutes on that, so I didn't put them up here, but all the work I'm going to be showing is the hard work of my research group. So again, on the same theme that Dave had said, a lot of my career has been based on analyzing CloudSat and Calypso, which was actually part of this really sort of one of its kind, I would say, train of satellites called the A-Train. Provided us with information about the energy cycle, the water cycle, carbon cycle, you name it, all aspects, even the surface properties, all in one big suite of satellites. And so I've done quite a bit of work on that. Using those observations, what I'm currently looking at is a little bit in line with also what Dave said, but from a different perspective. Trying to look at what these observations are telling us about convection, and in particular, what it's telling us about the radiative properties of convection. There was this interesting result quite a few years ago now, maybe almost 30 years ago, that when you look at a convective systems, at least in the tropical West Pacific, the reflection of shortwave radiation tends to cancel the trapping of longwave radiation almost perfectly. And so these systems have basically no radiative effect in that one particular region of the Earth. That's not true all around the Earth. And as the climate changes, the effects, the shortwave and longwave effects of these clouds may change due to the storms becoming more intense. That's typically the way we think it's going to go. So my research is focusing now on how do you relate convective intensity to the radiative properties of these clouds, and we're trying to understand how things might change in the future if they become more intense. This is a little bit more historical. This is work that a PhD student named Alex Mattis, who's now at the Goddard Space Flight Center, did with me. This basically just illustrates the value of some of these sensors. What we were trying to do here is actually just understand what role do different cloud types play in Earth's energy budget. So a lot of sort of the historical work has looked at what you're seeing over here, which is kind of the net effect of all clouds on the radiation budget. We're looking at the top of the atmosphere here and the surface here. We broke it down into ice clouds only, which tend to warm the planet over a large portion of it. Liquid clouds, which tend to cool the planet. This again aligns a little bit with what Dave just showed. And then in particular, this CloudSat and Calypso combination was really good at determining clouds that were made of both liquid and ice, mixed phase clouds. And so we were trying to understand what contribution do these mixed phase cloud regimes actually make in our climate. And the interesting result here was that even though they only make up about 8% of total cloud cover, mixed phase clouds contributed about 20% to the total cloud forcing at the top of the atmosphere. So that's just a little highlight from some work I did with a student a few years ago. Lately, my work has started to focus a lot on polar energy budgets, kind of looking at the changes that we're seeing in the Arctic, but we're also starting to now see changes in Antarctica and trying to understand how the different radiative exchanges in these regions are driving those changes. So here is a little cross-section of some of the recent work in my group. Hamish Prince is looking at the energy balance in the Arctic. What you're looking at here, the green lines on both of these plots, is what's happening to sea ice in the Arctic since 2000. And he was using top of the atmosphere radiation measurements to show that indeed, as the sea ice declines, you do see the Arctic absorbing more solar radiation. So, you know, the whole idea of an Arctic amplification where the Arctic warms up in response to more solar radiation. But he also found that, interestingly, as the Arctic is warming up, it's emitting more energy back to space as well. And it turns out that they're doing this at almost the same rate, and the net energy balance of the Arctic is actually not changing, or at least not in a statistically significant way. Claire Mundy, another PhD student in my group, both Claire and Hamish are getting close to graduation. Claire has probably about a year to go. She's looking at how Arctic cyclones interact with sea ice and, you know, maybe accelerate the rate of decline here you're seeing in the green curve. And so that's just an animation of a cyclone interacting with the colored contours, which are sea ice concentration. And if you look closely enough, you can see the cyclone as it interacts with the sea ice here, starting to erode some of the ice, as you might expect. So she's trying to quantify that effect and see how it's changing in a changing climate. Carissa Shannon, recently graduated master's student in my group, is looking at the contributions of snowfall to the Antarctic ice sheet, and I'm trying to understand what role extreme snow events, heavy snow events play in Antarctica. And then she's taken that work a step further, and what you're looking at here is the synoptic conditions. This is a pressure anomaly that leads to the extreme snow events in this particular basin. And what she's found is that really almost no matter where you go on Antarctica, there's always this consistent pattern of a synoptic pattern that drives moisture onto the continent is responsible for a lot of the extreme snow, which is also responsible for a lot of the mass change on the continent. And then finally, Cameron Bertosa, recently graduated PhD student in my group just last month, was looking at the types of, well, basically the impact of clouds in the Arctic and this interesting phenomena that the Arctic, and Antarctica as well for that matter, seems to have this kind of bimodal distribution of cloud impacts on the surface. It's either kind of transparent, and it just looks like a clear sky, or the clouds have a significant impact and significantly enhance the amount of radiation incident on the surface. And so he's been looking at why that happens, where that happens, what times of year that happens, and do models capture it. And the green lines on here, so the bars are the observations, green lines tend to be different reanalyses. You can see that the reanalyses are kind of all over the place with respect to the measurements. Okay, so in the last second here, I want to talk just about the recent work in my group, which is this pre-fire project, really cool experiment that we're doing where we've launched a couple of CubeSats into space with the idea of mapping out the entire emission spectrum of the Earth, including that region in blue, longer than 15, wavelengths longer than 15 microns that we've never measured before. And so I know I'm getting to the end of my time, but I want to just show, and I don't know if the sound will, Pete, will the sound work on this? Okay.
Should.
So this is a video I have not yet shown in this building, but this is a video of the launch of Pre-Fire that was put together by Rocket Lab, the company that launched us. There we go. So this will be the launch. So you can see the rocket going up. This is an Electron rocket launched from Mahia, New Zealand. And then what you're going to see is the next part of the video. Set the music. Again, Rocket Lab, not me, but I like it. They're going to show the first stage cutting off. And then you're going to see the release of the first stage, and then the ignition of the second stage. And that's the rocket that actually put us up into orbit. This engine put us into orbit. They told me before launch that that was the most critical stage, that if that doesn't go right, and the first rocket doesn't drop off, the whole satellite mission is going to go into the ocean and die. So that's when we celebrate it. But here, this is maybe not quite as fancy, but this is even cooler to me. This is the picture of our CubeSat actually being deployed from the launcher. This was on the top of the rocket. And you see this is a real video, not some artist's conception. This is the actual injection of the satellite here with the real Earth, you know, sitting there in the background, but we're in space here. That's the deployment of pre-fire. And then finally, here's our first glimpse at some data. This is a first light video that was created by NASA showing real data. This is 1 day of data from one of the 2 CubeSats that we launched as part of this project. And they're basically showing some of the science that we're doing. We're looking at intersections of orbits from 2 satellites to try to understand how various processes in the polar atmosphere affect that emission spectrum of the Earth. And so this video will just show, not to get too deep into radiation, but what you're seeing here is how the different wavelengths basically sample different layers in the atmosphere, and so you kind of understand the different, what's happening at different heights in the atmosphere using these measurements. And I'm actually right on time, which is unusual for me. So I will show my last slide, which is to also add that I am also the director of the Cooperative Institute for Meteorological Satellite Studies, another amazing asset that we have in this building. What this particular slide is showing is that we have been around since the very start of essentially satellite meteorology. We are the birthplace of satellite meteorology. And we have data archived all the way back from the geostationary record all the way back into the 70s. And we're continuing obviously forward here with GOES 19 now. We also have a variety of low Earth orbiting satellite data and a tremendous amount of expertise for reading, processing, interpreting those data. So this is one of those assets that if you're in the building, regardless of who you're working with and what project you're working on, if you ever have a need for satellite data, this is kind of the place to have it. So now I think I've used up all my time. So.
We have time for a short question for Tristan if anyone wants to ask anything. On to Andrea.
Okay. I will hopefully get you out of here on time, but we'll see. So I'm Andrea. I'm also on the 15th floor. I think we're getting a good tour of faculty from the 15th floor today. I am interested in, basic science questions, but also applied science questions. So some of the things that I didn't include here in figure form or anything is that I'm really active in the AMS, and some of my activities in the AMS are really with the applied side of our field. So I'm the chair of the AMS board on enterprise economic development, and our board also includes things like the AMS Energy Committee and the AMS Weather and Climate Risk Management Committee and road weather transportation. So it's all these ways that our science is applied in other fields and other sectors, and how it helps inform decision making in those sectors. So that's a whole.
What's AMS?
AMS is the American Meteorological Society. Thanks, Dave. So that's one of the things that I wanted to mention. So I've had a few conversations with people about sort of like, what do I do next? And I'm thinking about that, and I would like to inform people via discussions or anything like that. But about science. So my group, I am new faculty here. I spent a little over a decade at the University at Albany, where my research group primarily is. I have a couple students that are graduating this year, so they didn't make the move out to Madison. But my research group, so we do a lot of Zoom meetings since they're still in Albany. But these are my current and former group members. And we think about a lot of things. We think about the extratropics, particularly wintertime, thinking about dynamics and variability in the wintertime atmosphere. We think about it from large scales, but also I think about it from how the troposphere and stratosphere are coupled together. And I like to think about this on time scales of weather systems, days, to also a couple weeks, so up to a season. And so some of the questions that we like to think about are things like this. So I saw this headline on Friday and I was like, oh, this is perfect. The polar vortex is acting weird and the US is paying the price this winter. And so this is my research in a nutshell. I think about how things in the stratosphere impact the weather in the troposphere. So I like to think about the ways that maybe the polar vortex is getting weird. So what does that mean? There's a lot of different ways we can define that weirdness. and the impacts, or how we pay the price. So in thinking about some of those things, I mentioned I'm thinking about timescales of a couple days to weeks. And so really what that is thinking about this sub-seasonal to seasonal timescale. And so one of the things that we don't do great, but there's room for improvement on, is thinking about prediction at these timescales of a couple days to weeks. And so this figure is a lot, and that's the whole point of it, is that there's a lot of things happening that impact the variability that we experience on timescales of days to weeks. And so there's things that are happening in the stratosphere. So here's my little stratospheric polar vortex sitting at the top, you know, like a crown. So it's very, very important, and you should all be thinking about it. But there's also things like ENSO, and Dan has thought about some of this on that timescale. There's things like, how do these types of variabilities impact the atmospheric rivers that make landfall on the West Coast? So Dave mentioned MJO, that's in there. So there's a lot of different things that contribute to variability on this time scale, but the one that I'm particularly interested in is how variability in the stratosphere impacts the troposphere. So instead of showing figures, I decided to put a conceptual model that puts all the things that I'm interested in all in one big package here. So some of the things that my group is thinking about is how the stratospheric variability and how extremes in the variability in the stratosphere impact the weather that we experience living in the troposphere. And so one of the projects that we're working on is thinking about how stratospheric extremes impact cold air outbreaks that we experience in the US. So polar vortex is getting weird and we're paying the price. So we think about how variability in the stratospheric polar vortex, and so this is, we can think about this as the winds that are roughly 30 kilometers above Earth's surface in the stratosphere. And there's a big circumpolar circulation that develops every winter time, and it can be really strong, or it can be really weak, or it can wobble off the pole or meander. And so all of that variability can inform the things that we might expect living in the troposphere. And so what we found is that there's different types of variability that particularly impact cold air outbreaks in the US. And so one of the things the media picked up on is that there's these things called sudden stratospheric warming events that supposedly produce cold air outbreaks in the US. And our research shows that that's not really the strongest type of variability that produces cold air outbreaks in the US. And so there's this other type of variability called stratospheric wave reflection events. So that's a weird thing to think about. But what we're looking at in this figure is one of these wave reflection events. And these are, if you imagine a Rossby wave, and so there's these waves that travel along the jet stream. A Rossby wave, you can think of, comes in a wave packet, and there's really big wave numbers in that Rossby wave, a really large waves, so these are the planetary scale waves, and then there's the smaller scale waves. So you can have the planetary components of that Rossby wave packet propagate upward in the stratosphere, and that's what this diagram is supposed to represent, is that you can have a component of that Rossby wave packet propagate upward over Siberia, for example, interact with a reflecting layer in the stratosphere, so that wave packet is reflected back downward into the troposphere. And so this Rossby wave reflection, there's a number of ways we can quantify it, and our research group is thinking about some of those things. But what we found is that these wave reflection events tend to be more linked to cold air outbreaks in the US. And what we found is that the duration and the area of cold air outbreaks associated with these wave reflection events are significantly larger than just your run-of-the-mill cold air outbreak without a wave reflection event. So that's some of the things we're thinking of. And it turns out that we can actually look at these things in reanalysis data. We can make a forecast of them. It turns out the GFS actually, if you look at a forecast in the GFS, they get these wave reflection events. And so what you're looking at in this is a cross-section, average between 45 and 75 degrees north, and it goes across the entire northern hemisphere, and this is an example of one of those wave reflection events in real time. So that's one of the things that we're thinking about. Another thing we're thinking about are how stratospheric extremes, so variability in the stratosphere, impacts variability on the tropopause. And so we're thinking about these are tiny little tropopause polar vortices. They're synoptic to mesoscale features. And you can identify them on maps of the dynamic tropopause. That's what this figure is. Everywhere you see the purples is cyclonic circulations on the tropopause. And this is a map one of my former students, Tomer Berg, maintains a really great real-time weather page. And so he was part of a project where we were thinking about these tropopause polar vortices. And what we found, and one of my students right now is doing his PhD, he's about to finish his dissertation, thinking about how stratospheric extremes influence the location of these TPVs. And we can see that it changes their location. And these TPVs, because they're upper level vortices, they sort of are precursors to weather we might experience at, sometime during the winter season. So that's one of the things that we're thinking about. And we're also thinking about how these things together, Rossby wave reflection, TPVs, being changed in their locations, influence the mid-latitudes and the location and preferred regions of things like Rossby wave breaking, which can lead to blocking events and all these things on subseasonal timescales. So these are some of the things we're thinking about, and we're thinking about these all in separate projects, but I'm really excited because it looks like, and I know I only have a few minutes here, but it looks like funding is maybe gonna actually work its way through for a field campaign. So here's my little plane, where we're gonna be flying to actually observe these TPVs on the tropopause when they're interacting with the mid-latitudes while the stratosphere is doing its thing. So I'm really excited that this project is, hopefully the money gets here next week, that's the word, if things don't change. But we're gonna be using, for the first time, NASA's new Boeing 777. It's currently going through all these processes to get instruments on it where we can observe all of these things happening at the same time. It's a big collaborative project. It's gonna be at the same time as some of our colleagues in Europe who will be taking observations downstream on the other side of the Atlantic. So I'll end there.
All right, any questions for Andrea? Are there any announcements for visiting students that they need to know? I know that their next step is dinner at 6 where they're meeting in the lobby, but Dan?
If anybody wants to go on a tour of the roof after this,
Yes.
go up there.
So roof tour immediately after this, and then I know for dinner for visiting students, meet on the first floor lobby at 6 p.m.